1, you're live.
All right, so I believe we left off about here on the day one presentation that's spanning into day two here. So I wanted to do just a real quick recap on the stuff that we covered last Thursday, which was a high-level overview of transmission lines, their physical properties, electrical properties, how we model transmission lines in the power system, and for fault modeling and the type of work that we do for relay settings analysis. And we just started getting into a little bit on the fault response of what happens during a line fault, and then a little bit into the protection aspects, which is really the goal of what we wanted to present here overall. So, we're going to pick up there, but before we start talking a little bit more in depth about line protection, I wanted to see if anyone has any questions from the stuff we covered last week. All right, not hearing anything. We'll kick things off here with a little bit more of the protection overview. So really, kind of the goal for today, and I apologize, I'm halfway through a slide deck. I usually try to do a agenda for anything like this. Of here's what we're going to cover today. I only made it about 2/3 of the way through my presentation last time, so we're going to pick up from there. The other third that we're going to start on this slide deck is really just doing some very high level overview of line protection considerations, types of schemes we might apply, and very much at a high level. Then we'll move from there. That hopefully shouldn't take the whole class today. We'll move from there into the day two slide deck that I think Paul just mentioned he had posted. And that's going to go into a little bit deeper dive into one of the most common line protection schemes, which is a step distance protection scheme. And we'll go through, what step distance is, how to configure it, what the philosophy behind how you select and configure the settings for that scheme. And then I doubt we'll have time today, but the second half of that slide deck is going through a calculation example. Paul did ask I come up with a homework assignment, so probably next class I will have a homework assignment for you all going through a similar calculation example to the one that I'm planning to go through on the kind of second half of that slide deck on the step distance protection. And then, the last handful of slides on there is really going over some kind of unique considerations for, maybe some more advanced considerations and stuff you need to look out for with step distance schemes. And then the day three slide deck, which will probably be, start next Thursday and finish up the following Tuesday, is going into pilot protection, which is kind of an interesting approach, a little bit different approach to line protection, where the relays at each terminal communicate with each other to share information and make a better informed decision about whether or not the fault is on the line or not on the line, or if they need to make an operation. So that's kind of the plan for today, and then beyond, to wrap up the transmission line protection portion of the class. So I'm going to start back over here and just quickly go over a couple of things we talked about last time, and then get into the protection stuff in a little bit more detail. So, as I mentioned last time, if you do have any questions, jump right in and ask them, go off mute and get my attention, and I will, I'm happy to answer anything that you have for questions as we go through the content today, or really anytime. So, all right, with that, I'll get going. So, one of the things we left off with last time is really taking a look at this transmission line protection here. So, generally, your line protection is going to be applied as a relay at each of the line terminals of your transmission line. So you'd have a station A on one side, station B on the other side, and each would have a relay set to protect the line and work together to provide clearing and full coverage for any fault on the line. So historically, these relays were a lot of very, electromechanical single function devices, but modern relays, it would be a single box per system, and they may have redundant systems. They might have two relays for one line, but they both be working in parallel with each other rather than dependent on each other. And within that relay, you've got multiple protection elements that you can apply for various line protection schemes. And this is the 421 overview here. And you can see we've got a whole bunch of different options for things the relay can do. And as protection engineers, we need to kind of sift through that and figure out what's important for the specific application. And generally, that means you turn off almost everything and pick a handful of applications or relay elements that will accomplish your goals to try to keep the protection as simple as possible. So the two I've got highlighted here, 21 is distance protection, and then 67 is directional overcurrent protection. And those are usually the two main schemes that you will very consistently see in transmission line protection. So the way we'd approach it as a protection engineer is to take a look at each of those schemes, each of the elements, and apply a protection philosophy to cover specific events, specific considerations that we need to try to protect against. And we need to make sure that whatever we provide has the right coordination to see all the possible faults, and it's coordinated with other system relays, because we want our relay to operate for line faults. We don't necessarily want our relay to trip for station faults or faults off of other lines necessarily, because that should have its own protection that should be responsible for clearing that fault. So, one of the things that gets complicated about transmission line protection is there's a lot of variables that we deal with as protection engineers. Not all lines are set up in the same way. They're not all physically the same. They may have electrical differences. They may have other things that we need to look at as protection engineers to make sure that we're providing a robust protection system that will cover all of those scenarios. So I listed a few of the things here, and we'll talk about some of this stuff in a little bit more detail as we go through the rest of today's class and the next couple classes. But one of the main things is there's all the different fault types that can happen on transmission lines. So 3-phase, single line to ground, line to line to ground, broken conductors, different things like that. And those could happen at any location across, a transmission line that might be tens or even, 100+ miles long. And we need to be able to detect any of those locations and fault types. So line length plays a big role. There's differences in protecting short lines versus long lines, and some other things you need to consider. And that's both the physical length, which is, measure it, Google Maps, you can measure out, okay, this is however many miles long, or the electrical length, which has some to do with the length of the line, as lengths, the electrical parameters of the line impedance are generally calculated as, impedance per unit length. So, however many ohms per mile or whatever. And there's also a factor of the source strength behind it as well, which drives, the SIR's source impedance ratio, which is what we call the electrical length of the line. So there's some other considerations we'll have to think about when we're looking at that. That source strength is also variable. So the source behind you that's driving the fault current and how the system electrically responds to the fault is variable, because you might have equipment outages, you might have generation dispatch, you might have other system changes that impact the currents and voltages the relay will see during the same fault. We talked through a couple examples of those and the questions we were talking through last week. Line loadability is a big one. We want, as protection engineers, we want our relays to operate for faults, but we also really don't want them to operate under load. If you're in a very high load condition, the last thing you want is to further stress your system by tripping your transmission paths off from a relay operation. So we'll talk a little bit more about loading later. A lot of the examples we're going to be talking about are going to be very simple two-terminal lines. So you've got two stations connected with a transmission line in between. They can get a lot more complicated than that. They can have multiple terminals. They can have tapped loads or tapped substations off the middle of the line that need to be considered. And there's mutual coupling impacts, which is one of the things we talked about with the electrical parameters, that you can have fault current from an adjacent line couple onto the conductors of the line you're trying to protect, which again impacts the currents and voltages that the relay sees. We've got CT and VT accuracy concerns. So, our current transformers and voltage transformers are what take the primary measurements from the system and step them down to something we can put into the relays. Well, if we start having CT accuracy issues due to saturation or VT accuracy issues, that will also have an impact on what our relay sees, because it's no longer accurately representing the actual primary quantities of what's going on in the system. So really all that plays into what we need to consider with how our protection is going to operate. And one of the other things we really got to be concerned with is how fast does the protection operate. So the transmission system, especially when you need higher voltages, has some really strict clearing time requirements. I'm working on a project now where we've got to fully isolate a station fault from a remote terminal in less than 8 electrical cycles. So you're talking about a small fraction of a second is how fast you not only need to detect the fault, you need to open breakers to clear the fault and send signals to the other end of the line to tell their breakers to do the same thing. So that, we're talking about very, very high speed systems here that are often driven by system stability and other clear time requirements. And then with the operate speed, we also have to make sure we're clearing things fast enough to protect, the equipment itself. And that's probably a little bit less of a concern at the transmission level, because everything has to clear so fast for the stability considerations that, you're usually less concerned about the equipment thermal capacities than you are critical clearing time of the system for stability reasons. And then when we go to plan what kind of scheme we want to apply, we need to think about, what's available for communications between the stations on the line. So some of the first schemes we're going to be talking about are called step distance schemes that don't rely on communication. But if you want to do some of the more advanced schemes that have some security and reliability improvements and speed improvements, you might need communications between the two relays to be able to provide a certain type of protection that you might be looking to do. And then lastly, is there a need for backup or redundant systems? So what happens if one of your relays fails, or one of your breakers fails, some other piece of equipment fails? How is your system going to be protected? Because you still have to meet all of these same considerations for any kind of failure operation. So there's a lot of stuff that as protection engineers, we really got to spend a lot of time digging into the details on the line protection aspects. And A lot of the stuff's not unique to lines, but it does become a bigger impact with lines because it is a very complex system with a lot of things to think about. So before we dive into line protection specifically, I wanted to talk a little bit about protection system objectives overall. As relay engineers for any protection system, we've got some kind of core objectives that we're trying to meet. And these are listed here. So generally, when we talk about any kind of protection system, we can frame why we set a protection element or a protection scheme, how we did, with these terms. So the first one is reliability, and it's the assurance that a protection scheme will operate correctly. Now that's broken into two pieces that are have opposite priorities. So dependability is the degree of certainty a relay system will operate correctly, and security is the degree of certainty that a relay or system with relays will not operate incorrectly. So in a way, it's saying the same thing. We want the relay to work properly. But generally, when we're talking about a protection element, we can kind of define some limits of security limits and dependability limits. And ideally, we can find a set point or a way of setting it that meets both of those criteria. And that's not always the case, because sometimes you're going to run into a situation where you're sacrificing dependability to gain security. So you may not operate for everything, but you're not going to trip when you're not supposed to. In general, the philosophy I see most relay engineers use is to prioritize dependability. Make sure the relay is going to clear every fault it's supposed to. The more dependable you make the scheme, the less secure the scheme becomes, because the more things that it will operate for, which increases your dependability, means there's more things that it's possibility that it's going to operate incorrectly for. So that's a really big one, especially in the transmission system. There's a lot of reliability standards, a lot of reliability requirements. Utilities have to report on it. They get audited on it. There's a lot of stuff that goes into system reliability. It's a very big thing on the transmission system. Selectivity has to do with maximum continuity of service with minimum disconnections. So we want to make sure that we're operating for line faults, because that's what we're supposed to trip for. But we're not operating for faults in other parts of the system, because you trip the line out without there being an actual problem on the line. So that gets into some of the stuff we're going to talk about coordination and how we approach making sure that the relay's operating in sequence and in coordination with the rest of the surrounding system. Speed is minimizing your fault duration because of equipment damage and system instability. So we talked about that a little bit on the last slide, that we got to operate really fast on the transmission system to meet that objective. And a couple of the other ones that seem to always kind of fall at the end of this is simplicity, really making the system as simple as possible while meeting the objectives. It's very easy to fall into a mode where you do something overly complex. You've applied too many protection elements because you think you're covering everything, and it's going to increase these other metrics of reliability and selectivity or speed. But the more things you apply, the more things you have a chance of misoperating. So, or you make things so complicated people can't understand it, and it makes things more harder to work with overall. So in general, it's always a good idea to keep things simple. And we as engineers like to fall into the trap of making things more complicated because we think we can outsmart it and cover everything. And every time I've done it, I've regretted it. And I always come back to simplicity as being very important. And finally, economics. We need to factor in what the cost of the protection is in general. These days, utilities have pretty deep pockets for spending money on improving reliability. There's a lot of money being spent in the power system today. So, but that doesn't mean it's a blank checkbook. If it's something that you're coming up with a solution and you've got to install 20 miles of fiber optic cables to get a signal from one station to the other station because you can make some small improvement in these other things, you got to weigh in that economic value. Is that something that's worth it to the utility to spend that much? It could be millions and hundreds of thousands or millions of dollars to make this this change. Is it worth it for the economics? So all these factors are things that we're going to want to think about as we're going through and selecting any protection scheme. I'm going to try to frame a lot of the stuff we talk about in the protection discussions with these terms. So I want to make sure that it was we went over those in some good detail. I guess any questions on these protection system objectives before we move on?
I was just curious about redundancy. Originally, we talked about having a relay at each end of the line. Would you ever see a situation where they have redundant relays at each end of the line, or is that overkill and breaking the economic end?
Historically, it was considered overkill. These days, almost every utility I know of applies redundant protection at the transmission level. So certainly at 115 kV and above. Some even do it at 34, 60, 69 kV, things like that. Because there's a lot more constraints on reliability these days, that when you go to operate your system, you need to be able to operate it, for the day that you have to take that relay out of service to do maintenance testing on it. You need to cover the case where, these are very robust electric devices, the relays, but they do fail. And the equipment that is giving them the information fails, or CTs or VTs could have problems. So pretty much almost all of the time, you will see redundant protection applied at the transmission level. And that goes for almost any protection system, whether it's bus protection, transformer protection, and certainly line protection. And there's a really, really interesting IEEE guide that just came out, and I can probably get you the number if it's something anyone's interested in. But it's a guide on the considerations for redundancy and in protection systems. It goes through a lot of analysis and discussion of the impacts of redundancy on reliability, because redundancy, has a very big positive impact on dependability, because now you've got two systems of relays that will both see a fault and will be there to operate properly for a fault, and you're covering all these other scenarios where you could have some failure that would prevent that from happening. Redundancy has a negative impact on security, because in the same way you've got twice as many things that can operate when you want them to, you've got twice as many things that can operate when you don't want them to as well. But in general, if you go through the math and probability behind it, and that kind of thing, you can show that you get a pretty big boost in dependability for a small sacrifice in security in applying redundant protection. And actually, when you get to a BPS site, which is a bulk power system site, in general, it's all of our 345 kV stuff in New England, as well as some 115 or 230 kV equipment. There are some other regulatory requirements that require complete redundancy of everything. So you have to have redundant relays fed by redundant CTs and VTs, operating redundant trip coils in your breakers, fed by separate battery systems. It's complete. If you put the two systems in two different buildings, you could, drive a truck through the panel lineup of one, and the other one would still operate with, no interruption of service. That's the rigor that they put into the redundancy requirements at the bulk power system. But that's not required everywhere. It's just it's really just for those really critical facilities. So great question. Appreciate it. And any others? Well, all right. Well, we'll get into some of the other protection stuff. So, one of the things I mentioned was selectivity. So we want the relay to operate for faults that are in its protection zone. And ideally, we don't want it to operate for faults outside of its protection zone. So the example down here, the relay, really either of these relays, either the relay at station A or station B, should not operate for this bus fault because there should be some bus protection over here that will clear that fault. And, we don't need to trip the line off for that scenario. So there's really two ways we look at selectivity. We can, and it's all considered coordination. So we've got to basically coordinate these relays with the other surrounding relays to ensure that they don't, that we give that other relay an opportunity to trip. And there's two ways we go about that. One is through sensitivity. So we could set the relay at station A, so it just will not respond for a fault on that bus or for a fault somewhere else past this bus. So we can coordinate with that by just having it not operate, because that's what it's not supposed to do. Or we can use, things like directionality to make it so that the relays, don't operate for a fault in that direction. So the relay here at station B is a line relay, should be looking forward towards the line and operate for line faults. The directionality makes it such that it's only going to operate for faults in the direction of the line, and it will not operate for faults behind it. So that's a couple methods that we can coordinate the protection systems using sensitivity. The other option, and it's usually a mixture of these two, is coordinating using a time delay. So, we would delay operation of the relay here at station A. It would see the fault, but we'd make it wait for long enough that the protection for the bus protection at station B to detect the fault, make a trip decision, clear its breakers plus some margin to make sure that we're allowing that relay to clear the fault rather than, a relay that's not the primary protection for that piece of equipment. And that's usually done, the timing is usually done with either a definite time delay, which is a fixed delay. Okay, so we're going to wait 30 cycles or half a second for this relay to trip for a fault it sees at that bus, because within that 30 cycles, the bus protection will clear the fault. If it doesn't clear the fault, well, we'll still trip, but we're at least giving it enough time delay to do that. The other option, you probably talked about the inverse timing and the distribution presentations last week and the week before, is using an inverse time delay. So basically we adjust the timing of the relay based on the magnitude of the fault current that the relay is seeing. So, if the relay sees a higher current, which would be, more common for a fault closer to the relay, it'll operate faster. And if it sees a lower current for a fault that's further away, it's going to operate slower. So that the coordination and inverse time characteristics gets a little bit more complicated, but it's a pretty handy tool, because with that same element, you can be operating fast for things that are close and slower for things that are further away, which meets that kind of coordination through time delay objectives. So with the distance protection and the directional overcurrent protection that we would apply, we're going to be using a mixture of adjusting the sensitivity of the relay elements we're using and adjusting the time delay on those elements. So a couple other terms before we get into a little bit more on some of the protection stuff is some of the terms we'll use for our protection is overreaching or underreaching elements. So a overreaching element is a line protection element that will operate for faults past the end of the remote terminal of the bus or of the line. So an element that would operate for that fault at station B would be considered a overreaching element because it will see through its sensitivity, will see a fault past the end of the line. And an underreaching element is one that's set so that it stops operating at some point before the end of the line. So, it might only reach halfway or 80% of the way down the line, but it won't see faults in the last portion of the transmission line because you can't, it would typically be set high speed or no intentional delay. And if it sees past the end of the line, you lose that selectivity and the coordination that we're trying to achieve. The other things we'll talk about is forward and reverse elements. So as I mentioned, directionality comes into play a lot on transmission lines because you're going to see on the distribution system, for the most part, your fault current is all flowing in one direction. You've got a source at the substation, and then it flows down through the distribution system. And if you get a fault on the line, you've primarily only got fault current flowing in that one direction. The increasing distributed generation and things like that. More complex distribution arrangements, that does change that a little bit, but in general, we're talking about radial protection, all the stuff's going in the same direction for fault currents. And we don't have to worry about directionality as much because it's kind of built into a radial system. So in the transmission system, we've got sources on both sides. So if you remember the system equivalent, we've got a Thevenin equivalent impedance at station A, and we've got one at station B. So we're going to see fault current in both directions, depending on where the fault is. So usually we'll talk about forward or reverse protection elements, and it's defined by the CT location. So, when we configure the relay, we're generally tapping off of the CT in a way that, if you've got current flowing towards the line, it's flowing out of the CT and into the relay with that same phase relationship. So you're using your polarity marks and things like that to do that. So when we talk about forward, we look at the CT and we look at what orientation it is. And we can say that, okay, a forward for this CT is going to be faults on the line, and reverse is going to be faults behind the CT. So at the station bus, lines, whatever else is behind the station. And that's the same for each relay. So, it's what's considered forward fault current for a relay at station A is going to be different than at station B because the relay is looking in the other direction. So both relays, the forward direction is looking into the transmission line. Reverse direction is looking behind the transmission line back into the system. So we'll talk about forward and reverse elements a lot when we get into the pilot protection stuff, but we'll talk about underreaching and overreaching quite a bit as well. So I'm going to cover this stuff fairly fast, so you can use this kind of a reference, because we're going to dive into especially these distance elements a little bit more in my second slide deck. But I wanted to kind of give an overview of some of the typical stuff to expect to see when you're doing line protection. So phase and ground distance protection is very common. It's the phase is generally set and will only respond to faults involving phase quantities, so three-phase, phase-to-phase, or phase-to-ground fault. And ground distance protection is only going to operate for faults involving ground, so your single line to ground or two line to ground fault. Both will operate with an impedance quantity. So whenever we talk about any protection element, there's some quantity that is the driving deciding factor and if it's going to declare a fault or not. distribution protection, you probably talked a lot about overcurrent protection. You go above a certain threshold and there you go, you make a trip decision. With distance protection, we're using impedance. So we're measuring voltage and current at the terminal, and we're using that to calculate inside the relay an impedance quantity that we'll use for making a decision if it's a fault or not. So we need to outline current and voltage to do this scheme, to do this type of protection, and we'll use it in a step distance scheme or a permissive or pilot blocking scheme. The main difference between phase and ground distance is phase distance uses positive sequence impedance measurements, and ground distance uses zero sequence impedance measurements as the operate quantity. So which is what drives it operating for different kinds of faults. And both are inherently directional, are generally applied directionally, are usually applied using separate underreaching, overreaching, forward and reverse elements that work together to provide full coverage of the line. Some of the other stuff that you'll see very commonly is directional ground overcurrent protection. So this is very similar to the type of overcurrent protection you probably saw applied at the distribution level. That you're looking at zero sequence current. You're using a mix of instantaneous and inverse time delayed elements, and that'll either be used as a direct tripping element or as an input to a permissive or blocking type pilot scheme. We'll talk about a little bit more. Because it's directional, you need both current and voltage. So you're going to need the current for the measurement, but then you need something to determine which direction the current's flowing. So you need a reference. And typically we're using zero sequence or negative sequence voltage as the reference against the current, basically looking at the angle between the two, determine the directionality. But you can also use a measured neutral current, or there's a few other methods in there. But we're not going to go into a whole lot of detail on directional ground overcurrent protection. Again, it's very similar to the protection you probably learned about on the distribution classes. It does get a little bit more complicated with a grid connected system because there's a lot of different possibilities you got to cover, and so the radial protection makes that a little bit easier. But that's definitely something you'll see pretty commonly applied. We do not typically use phase overcurrent, and that has to do with line loadability. So ground zero sequence current is not generally present in a large quantity during load, because generally the transmission system operates at a fairly balanced load. So you don't have any zero sequence current to measure, or very low zero sequence current. So you don't really have to worry about your directional ground overcurrent elements operating under load, because there's almost none when there's no fault. And then when you have a fault, you've got very large quantities of zero sequence current for a ground fault. And that's not true for phase overcurrent. So, you certainly could apply a phase overcurrent element for transmission line protection, but you're really going to start hitting that limit where, you're going to either have to sacrifice dependability of the element because you've got to set it above the load current levels versus, or sacrifice loadability and not be able to put as much load through your line before it trips off. So in general, you really won't see a lot of phase overcurrent protection on transmission systems. Sorry, move the slide there. We talked a little bit about switch on to fault protection last class. This is really there. It's just enabled for a short time in the case that you've left your grounds on the transmission line and you re-energize it. Again, your directional ground overcurrent and your distance protection both rely on line voltage to make an operate decision. So if you don't have that voltage because you've grounded out your terminal, you're not going to be able to make a trip decision based on current alone with those schemes. This is added to that to cover that one very specific scenario. And then lastly, we've got line differential protection. This is becoming more and more commonly applied throughout the transmission system. And it's a scheme that uses a communications channel between the line terminals of a transmission line to allow the relay at one end to send measured current magnitudes and currents, magnitudes and angles from its terminal to the other terminal to basically apply Kirchhoff's current law for the transmission line. It's terminated at two lines. All the current going in one side needs to equal the current going out. So by sharing those measurements between the two terminals and synchronizing the measurements, you can make a very accurate determination if there's a fault, if the fault is on the line or not, because you're looking at all the currents into and out of the line. So we'll talk a little bit more about line differential, assuming we don't run out of time on the last line protection class here, but it's definitely something we see a lot more of. The other thing we're going to talk about in a little bit more detail on the day 3 slides is pilot protection. So a lot of the schemes we apply are just relay elements at one terminal looking and saying, is there a fault or not, and making a trip decision based on the information just at that first terminal. What a pilot scheme does is it shares some amount of information from each of the terminals to the other terminals. And this could be as simple as one piece of information of the relay saying the fault is in front of me. And the other relay receives and says, hey, the fault's in front of me too. It must be on the line because it's forward in both relays. Or it could be something more complex like the line differential scheme that we'd apply. But that really relies on this transmission communications path to get that information, be it a single bit of data or a stream of high accuracy current measurements from one terminal to the other. It relies on that communications channel. So we'll talk a little bit more about that. And usually the pilot protection, the main advantage is you're operating faster. Because you can make a more informed decision about where your fault is, you can increase the speed without sacrificing reliability, or more specifically, without sacrificing security of the scheme. Pilot schemes are usually provided in parallel with another scheme to cover the case or what happens if your communication path fails. So usually we'd apply all those other schemes, your directional ground overcurrent, your step distance scheme, switch on default might be applied in the same relay, but in parallel with another scheme for the pilot protection. And here's just a list of some of the different types of schemes that you'll see as different types of pilot schemes. And we'll talk about those a little bit more when we get to that day 3 class, and I'm already running longer than I would have anticipated, so I probably should get going on it. So this is really the end of the first set of slides here. I provide some additional references on here that I thought were pretty handy. IEEE Guide for Protection of Transmission Lines is a great resource for folks learning about transmission protection. This transmission line settings calculations beyond the cookbook by Mike Thompson and Daniel Heidfeld is an excellent entry-level technical paper that Schweitzer put out on general considerations for line protection, and it's written from a very practical relay engineer standpoint, rather than too deep on all the technical math behind everything. And it's a very great paper. I recommend it for all my new engineers who are just starting to learn transmission protection. And then the protection relay and principles and application book by Blackburn is an excellent resource for anything protection related. So I thought I'd put those on there. I always like to put some additional references on anything. So we're going to get into the next slide deck. But before we jump into the day 2 slides, does anyone have any questions on the stuff I presented so far today? All right, well, I'm gonna jump right into the next one then. I was really unsure if my slides were enough, and I was going to be ending early, or I should have known better that I'd be on the other side of it, and needing more time. It seems that's how it always goes. So yeah, I'll dive right into some of the stuff on the day 2 slides here. What I really wanted to cover today was distance protection and step distance schemes. So I touched a little bit on distance protection on the previous slide deck. And we're going to go in a little bit more detail on how we use the distance protection elements to fully protect a transmission. So kind of the agenda of what was going to be day 2, and this kind of now second half of day 2 and into day 3. The recap of what we covered so far. And I'm happy to stop at any point. If anyone has any questions. We're going to talk about the distance elements, kind of fundamentals of what goes into a distance element and how they're applied, how we model them, what they look like, and how we view them and see them as a protection engineer through simulation software. And then we'll go into a little bit about step distance schemes and the philosophy of how they're applied. Talk about some other considerations and things that go into more advanced considerations for step distance protection, and then a step distance settings example. So I don't think we'll probably get to the settings calculation example today. We only have a little less than a half an hour left. So I'll probably try to get up through the step distance philosophy section, find a good break point there. So we already kind of went over the recap. I'll open it up if anyone does have any questions on anything. I just asked that, so I don't imagine anyone does, but any questions before we move on? All right, good. Well, not good. If I'd answer questions if you have them, but just following the slide here. So we talked about the protection system's objectives just a few minutes ago. So I'm going to skip over this slide, but I put this slide into every single presentation and training I do for anything. I copy it word for word exactly how it is, because as protection engineers, if you can take nothing else out of this class other than, if you start working in protection, to think about these aspects when you go to apply anything and ask questions, whether just to be this to yourself or to a mentor or someone you're working with in relation to these topics, you're going to turn into a really good protection engineer if you can think in these terms. It's very easy to go out and just apply things. But if you can explain them using these terms, you're going to really sound like you know what you're doing, because you will. You'll be able to really navigate unique considerations that come up, because you'll be able to frame them around these protection system objectives. So now we also talked about these same terms. So I'm already making great progress on this second slide deck. So we'll get into some new stuff here. So distance protection fundamentals. So I'm sure other presenters throughout the course here have talked about the IEEE function numbers and how we describe protection functions with primarily two-digit numbers to make it easier to look at a drawing and understand what a relay is doing. The IEEE function number for a distance element is 21. So you'll see that very commonly used in relay names associated with line protection or descriptions of protection elements and things like that. So you'll see that throughout this slide deck and beyond. So again, the distance protection operates using a measured voltage and current going into the relay to measure an apparent impedance seen at the relay location. So, the relay here, we're measuring line voltage, we're measuring breaker currents, the directionality of the relay is looking onto the line. And the relay for any fault or non-fault scenario is going to be calculating an impedance based on that voltage and current. So it's got these two operate quantities and measurements. And internally, the relay is going to be calculating an impedance, and then we're going to configure it to say, this type of an impedance is likely a fault, and it's likely a fault in this location. So we can make a trip decision based on that. It's called out as distance protection because in general, where we're operating with an impedance and the impedance of a transmission line can be described as a certain amount of impedance per unit length, you can roughly say that your distance protection is going to operate for a certain distance down the line, whether it's expressed as a percentage of the overall line distance or even a mile. So you can use distance protection to estimate where a fault location is, and the relay can say, oh, well, this is a 14-mile long line and the impedance was half the line impedance. So that means the fault is likely somewhere around that 7-mile mark, half the distance of the line. So that's where the term distance protection comes from, because when we're setting the elements, protection engineers, we're really considering how far is this relay going to reach, and we've got some good boundaries on it. Where things like overcurrent and things like that, we can't draw as tight of a boundary on how far an element will operate because it's going to be variable as the system strength behind us changes. Distance protection isn't a standalone, you go set one element, you're done thing. You're applying several elements to provide full protection of the line, both underreaching and overreaching elements, phase and ground elements. In some cases, you're providing forward and reverse looking elements to provide the protection scheme. We went over the same slide on the last one, but really, again, we're looking at phase distance operating with positive sequence impedance, ground distance operating with zero sequence impedance, and they detect specific types of faults. So that's really why you need both of the types of protection, or you need something covering phase and you need something covering ground faults, and they need to be considered separately as they they respond to different scenarios for the system. Similar to what I was talking about the ground overcurrent element not responding to load, your ground distance elements won't as well, because your measured apparent impedance at the relay is not going to respond to those load currents where you don't have a large zero sequence component of normal load in a non-fault scenario. Your phase distance elements will be load responsive. So, you're measuring positive sequence impedance. So there is an impedance that you'd measure that could operate for a load. So you have to be understanding of that when you're applying phase distance protection. We'll talk a little bit about how we can get around that if we need to later today or early on the next class. So, one of the things that's kind of critical to understanding distance protection, or really any protection, is what is my operate quantity going to be doing in a non-fault scenario, and what is it going to be doing, what's it going to look like at the relay for a fault scenario? So, really, I'm describing this for a distance element, but you kind of can think in those same terms for any protection element. What is this relay and operate quantity going to look like for a non-fault condition, and what does it look like for a fault condition? And ideally, we got a really wide difference between those two, and that allows us to have some flexibility in our settings. So looking at impedance as an operate quantity, we've got before a fault, kind of in your normal operating scenario. So in a pre-fault scenario, we're really looking at just normal system loading. So the voltage that the relay is measuring is going to be at or near nominal voltage. Your current is going to be driven by the system loading and how much load current is flowing through the line. You can kind of see that down here. We've got another different simplified view of the kind of power system with a Thevenin equivalent. We've got the relay, we've got the line impedance, and then in this case, we've kind of taken out the other terminal and just said, okay, here's our load. So normally, when there's no fault, your impedance relay voltage and current is going to be based on the voltage at the bus, driven by your source voltage and the voltage drop behind this Thevenin equivalent source. And then the current is going to be driven by, your load and your line impedance. And the load in general is going to be a much bigger factor to what you're seeing for current. But very simple circuit. You go through and calculate this if you have the parameters and figure out, okay, what's the voltage and current, and then what's the impedance that the relay is going to see in that scenario. So generally, we're going to have a fairly high impedance value for load type conditions. And the other thing we can look at is what's the power factor or the angle of that current that I'm measuring, or the impedance that I'm calculating. And in general, the apparent impedance that you're measuring at the relay is going to be fairly large and mostly resistive, because most of your system loading is going to be resistive. You'll be operating this plus or minus 0.9 power factor, give or take, something like that. So the way we can look at this is, the way we evaluate distance protection graphically is plotting it on an RX plane. So this is a plot you can generate out of Aspen or other fault simulation programs, or just calculate it manually. That you've got your x-axis is your resistive component, and your y-axis is your inductive component. So for a normal fault or a normal pre-fault condition, a normal loading condition, you're going to be operating over here with a fairly high impedance measurement from a quantity, and it's going to be somewhere in this shaded region over here that you're going to be operating and expecting to see load within this region. The circular shape in here is really driven by the magnitude of load, and then the place where it drops off here is when you probably say, oh, well, that angle is probably not load anymore. We're not expecting our load to exceed that angle or go below this angle. So we've got a pretty known quantity of what we're going to be measuring for non-fault conditions that, depending on loading, depending on what's going on, and we're going to be somewhere in this region. The more heavily loaded we are, the more current we have, the lower the impedance we're measuring gets, and the more lightly loaded we are, the higher our impedance measurement gets. So that's the load condition, or the normal operating condition. So what happens during a fault? Well, during a fault, the voltage decreases on the faulted phases. So if it's three-phase fault on the line, all three phases are going to have a depressed voltage measured at the relay location. And your current is going to increase, and probably increase pretty significantly, because now instead of the current at the relay being driven by the source impedance, the line impedance, and the load impedance. Now it's driven by a much smaller impedance quantity because it's just seeing the source, it's the source impedance plus the portion of the line impedance at the fault location. So current's going to go up pretty drastically when that happens. And then when you turn that into an impedance, you're going to see that, you know, the impedance is going to get measured impedance, the apparent impedance is going to get much smaller. And the angle in the impedance is going to move from this load region, you know, in that plus or minus 0.9 power factor region, to somewhere near the angle of the transmission. So I think one of the questions we talked about last time when we were talking through what happens, how does a system respond to a line fault, was what is the relay measure if you get a fault on the line? What kind of impedance would it see? And the answer is that it sees the impedance of the line, or the portion of the line that's between the relay and the fault. So where I've got this plotted here is, you know, roughly 50% down the line or something like that. And what we'd see is, you know, if the fault moves closer to the relay location, that fault location, the measured impedance, is going to move closer to the fault location. If it moves further away, you're going to see the, you know, that fault location, and the X where the fault magnet or the measured impedance is going to move further away. So for a fault outside of the line, maybe on an adjacent line off the remote end bus or something like that, you know, we might be seeing an impedance measurement that's, you know, further out here somewhere for a fault condition that's not on the line. But it's still going to meet these same things. You're still going to see a large increase in current. You're still going to see a voltage decrease, and the angle of that impedance is going to be somewhere near this kind of line impedance angle measurement rather than in the load region. So that's a really useful tool because, again, you know, as a protection engineer, we want a really big difference in electrical quantities, parameters that we're measuring between a non-fault condition and a fault condition. And that, you know, this really is one of the things that drives impedance protection, is a really, you know, great tool for transmission line protection.
Brandon, I got a question regarding the impedances. So now I don't have any direct experience with this, but so say like a tree fell on a line, would that be considered a high impedance fault? Yes. Yeah. So I guess is there any way to to I guess plan for that kind of fault?
Yeah, so fault impedance is definitely something that, you know, we need to think about as protection engineers. And, you know, I didn't go into a lot of detail on impedance, fault impedance in this, but some of the references I said will have that. But basically, you know, what you're going to see if you have a fault impedance, something like that tree falling, or arc impedance, or you know, something like that, you're going to have a new impedance that is in this branch here. So generally, your fault impedance is going to be resistive. You know, you're going to have, that tree is going to have a resistance associated with it. I'm sure it has a reactance associated with it too. I don't know how you calculate that, but it's mostly resistive. An arc is mostly resistive. So, you know, what you'd see is this red, fault location would have an impedance tied to it that would be mostly resistive. So now the impedance relay, instead of measuring the line impedance to the fault location, now the currents and voltages are driven by the line impedance and that fault impedance. So generally what you'll end up seeing in that case, if you do a simulation and include a fault resistance or fault impedance, is that this fault magnitude is going to drift in the resistive direction here away from the line impedance. So you're still going to see a drop in voltage, you're still going to see a rise in current, you're still going to see a reduction in the measured impedance, but the angle is going to be further and further away from this, this line angle here, which is a really important consideration when we start looking at how we actually, the characteristics of the relay elements that we're using. So that's a great question. Does that answer kind of cover what you were looking for?
Yeah, that just popped in my head. So I was like,
Yeah.
well, I was curious what that looks like. So I guess that this kind of scenario, I'd assume it's like a down line or something. I'm trying to imagine just what
So
this extreme fault might look like.
yeah, so most faults on the transmission system, they'll have some arc impedance, but it's not going to be a highly highly resistive fault or something like that. Sort of transmission line, utilities don't let trees grow near their transmission lines. They've got big programs to make sure that doesn't happen, and they maintain the right clearances because they don't want to have faults on their system. So it's less, that resistive fault coverage is maybe a little bit less of a concern in the transmission level because there's a bit more controls on it than, a distribution line next to the road that the tree could fall right on it. But it's still a concern, and you can still have arc impedance. But a lot of the faults are going to be things like, a line-to-line fault could be two conductors swinging in some intermittent wind and touching. That could be your fault. Or a lightning strike could have a short arc across an insulator or something like that. That would be your fault. And those don't really have a lot of your really common transmission line fault modes don't have a large impedance or resistive component to it to change this. So when you look at actual fault results and things like that, you'll see a little bit of deviation, but generally you're not jumping way off to the right. Especially on multi-phase faults, because single line to ground fault might have a bit more impedance, but if it's a multi-phase fault, it's usually just because electrically of how the fault happens, it's usually a little bit less fault resistance to it. But yeah, great question.
Okay, thank you.
So we've got a few more minutes here. I'm going to touch on a couple things about how we go about setting elements. I'll give a couple more minutes for questions at the end, and then we'll wrap up. And next class we'll do primarily talking about how to set the step distance scheme, which is really the next steps here. And then ideally we'll have enough time to talk about pilot protection on the last day of the line protection stuff. But so we know now that the impedance the relay is measuring has a pretty big change between non-fault and fault conditions. And generally when you're on the fault, when it's a fault, you're going to be, at a magnitude related to the line impedance, and the angle is going to be somewhere near the line impedance angle as well. So when we go to set distance elements, we're setting them based on a reach, which is, how far do I want the relay to look? How many ohms do I want the relay to look into the system? And that's generally set as a percentage of the line impedance. So this is an under-reaching element. You can see it's going to stop. So the inside of the circle will be impedance plotted inside the circle will be an operate for that element. That's where it says, yeah, that's I'm going to assert, or I'm going to time, or I'm going to do whatever. And any impedance falling outside the circle is going to be a no operate. So it's saying that's not something that I'm going to operate for. So the specific element we're looking at here is what's called a zone 1 under-reaching element, because you can see the reach of the protection. It's going to stop operating at this reach point, and it's not going to trip or make a protection decision for any impedance that's measured past that. So in this case, your transmission line here is there's more line after that this element is not going to operate for. So usually when we're plotting these on the RX plane, we're looking at this transmission line impedance. We're looking at the relay characteristic or reach. This is a Mo-shaped characteristic. And we've got a max torque angle of the relay element that defines, how how this circle aligns with the impedance. So, if you set the max torque angle for the element, the same as the line impedance, which is usually what you do, almost always what you would do, the line impedance will be across the diameter of the circle characteristic. But you could change it to something else. You could set it to 45 degrees, and this whole circle would tip to the side here, and the operate zone would be different. But in general, what we try to do is we set the reach, which defines the diameter of the circle, at some percentage of the line impedance, and the angle to match the line impedance, so that if we set this impedance at 80% of the line, like this one, we've got pretty good confidence that the relay is going to see faults up to around 80% of the line. And then faults past that, it's not going to operate for, which is getting back to that coordination through sensitivity approach to things. So when we go to set the element, we're looking at the reach, how far we're setting it based on ohms. So we're setting it in ohms as a quantity. We're looking at the angle of the element, which we can adjust. We're setting it as either forward or reverse. So in this case, this is a forward element. It's operating for faults on the line. If the circle was going in the other direction down in this lower left-hand quadrant down here, that would be a reverse element. And we apply those for certain reasons for different types of schemes as well. We're going to define a shape. So this is a Mo characteristic, which is a circular shape. You can also apply a rectangular quadrilateral shape, or a lens shape, which is like the circle, but kind of squeezed in a lens characteristic. I've only ever set one, maybe two lens characteristics in a couple quads before. Almost exclusively, folks use these Mo characteristics. And we're going to need to know, the instrument transformer ratios. So your current transformer ratios, your PT transformer ratios, in order to set this element. We'll do some math to calculate ground compensation factors. So generally, we'll talk about this a little bit more, but generally your ground elements are set using phase impedance set points, so that the phase and ground elements are set the same. But we need to tell the relay how to turn that set point into a zero sequence impedance. And we use some different factors, and they're handled differently in different types of relays. And then finally, we're going to provide some logic. So we've set this element. It's made a decision that, this is a fault. Well, that's a bit inside the relay that asserts to a logical one. We need to use that in relay logic to program the output contact or whatever other logical function we need to do when that element asserts. So just real quickly, and we'll pick back up here on Thursday. When we go to apply these elements, we're using multiple elements. So zone one element that I showed you before would be used in coordination with other elements, overreaching elements that would provide coverage for the rest of the line. And that's where we combine those different elements together. We turn them into what's called a step distance scheme, which is used to provide full fault coverage for the line, as well as coordination with the other surrounding protection by using time delay on the elements that'll see faults past the end of the line. So any of these overreaching elements. So I'll leave it there for today, and I'll open it up. I guess we get a couple of minutes if anyone has any questions, and then we'll pick back up here on Thursday.
I've got a question, Brandon.
Sure.
So what kinds of considerations do you have to think about for unfaulted phases that would see like a voltage rise when there's a fault?
Yeah, so in general, the distance scheme where you're measuring voltage and current and turning it into impedance, even if you have a voltage rise on that other phase, the the impedance measured, and how the relay looks at that is going to, I guess, cancel that out, that you got a higher voltage, but you're not having as much fault current on that phase either. So the impedance for that phase, or the phase to phase, and the way I'm going to go over distance protection is oversimplified to how it actually works. It's fairly complex how it goes on in the relay, because you're looking at, different distinct elements within a phase distance that, specifically target phase to phase, between A and B, or B and C, or C and A, and other things like that. So it's, just looking at this broad level is fairly oversimplifying it, but in general, it's good enough to do that. So I guess to answer your question, it's, it's certainly something that needs to be considered in the design of the relays, and it needs to be understood how it's going to operate. But it's not something we need to build into our calculations for the set points, but would be more likely to be something that would be flushed out when we go and do the set points, we do the calculations, and then we model it in Aspen or another fault modeling program, and run a bunch of faults to see how it responds. That should tell us how it's going to react to those different scenarios for in section or out of section faults. All right, any other questions before we wrap up? Well, excellent. Well, I appreciate you go through things with me today. And I really love the questions. A lot of really good, insightful questions today. So appreciate it. And we'll come back to it next Thursday and talk a little bit more detail about the step distance scheme. So look forward to it. Thanks all. Thanks a lot.
Thanks,
you.
Brandon.
All right, take
Thank
care.
you.